Hello everyone, I'm T. Madhrita from Aeronautical Engineering from Mahindra Engineering College. Today I'm going to present about the topic scarf repair technique, which is used in a composite aircraft structures to restore of structural stiffness and aerodynamic profile. The core idea is to remove damaged laminate with a shallow taper, then rebuild the original laminate architecture with matching repair piles and adhesives so load transfers gradually across a large bonded area. What is scarf repair? A bonded composite repair in which a damaged laminate is removed to create a shallow or tapered surface, that means the scarf, then rebuilt to match the original structure. The steps are: first, the progressive ply reproductions, that is, to replacement plies are laid into a tapered region, so fiber orientation and thickness progressively reproduce the original laminate. And second step is to gradual load spreading, that means the large shallow bonding interface spreads load over a greater area, reducing abrupt stiffness changes, a simple butt joint. Third one is a flush aerodynamic finish. That means after a cure, as the surface is a finished flush with the surrounding skin, preserving the intended external aerodynamic contour. Last one is governed by approval data. Used for structural composite skins and bonded components only when permitted by aircraft SRM or approved engineering data. And scarf geometry and load transfer. This will be given as shallow taper plus overlaying repair pills to give us a gradual load transfer. Here we see as this is the original laminate and here is a matched repair piles. Here design variables are the scarf ratio angle, which is combined by pile sequence, overlap, adhesive thickness, cure conditions and also a laminate material. And what are the procedure for scarf repair? The step-by-step procedures. First, inspect and map damage. We have to use a approved inspection model and determines its depth, size and affected piles. And second is the removed damaged material. To control the repair boundary while removing disbonded material, avoid extra fiber damage. And third one is the mission the scarf geometry. Mission or sand to a specified scarf ratio per the SRM or approved repair design. And fourth, we have to prepare a exposed fiber and we have to control contamination, moisture, surface roughness and bond line condition. And fifth one is a cut repair piles to reproduce the original stacking sequence and fiber orientation exactly. And sixth one is a place the piles and adhesives. Apply debulking or compaction and vacuum bagging procedures as specified. And cure the repair. Follow the specified temperature, pressure or vacuum and time cycle. And eighth one is a finish and inspect. Finish the flush, inspect the zone and perform required NDT or quality checks. And why this scarf repair restores stiffness? First, it matching the laminate architecture. First, its repair piles reproduce the original ply count. That is, the thickness and fiber orientation are like 0 degree, 45 degree and 90 degree. This will restore interned directional stiffness and large bonded area. The shallow taper provides a long transfer path, reducing abrupt load introduction and, and distributing stress across original and repair laminates. And for third is flush structural continuity. A correctly designed repair avoids a large external step or eccentric reinforcement that could introduce unwanted local bending. Here we should take a note of that for a laminate in plane stiffness is governed strongly by a fiber orientation or its thickness and material property. A thicker repair does not guarantee equivalent stiffness. And also the repair must be sustained for actual load cases, laminate layup, environment and bond line properties. The engineering target is to restore to a required or original design performance, not an unconditional guarantee of exactly 100% stiffness. And why it preserves the aerodynamic profile? Because the repair can be fired to original contour, avoiding the external step typical of many doubler repairs, and its reduced disturbance and also profile accuracy is matters. Here we are going to see that this is the original profile equal to a repaired flush profile, and this is a structure surface. This is a scarf required contour, that means it's a flush. And why select scarf repair for a full restoration because the original load carrying laminate is rebuilt rather than merely covered by an external patch, and also it gives a gradual stiffness transition. The taper reduces the abrupt geometry, stiffness discontinuity seen in a simple bed repairs. And efficient load transfer. The adhesive stress are distributed over a relatively large bonded area when properly designed. And matching ply orientation allowed load path to be recreated to a principal directions. And fifth one is that the repair can be finished to original contour, especially valuable on aerodynamic skins. And lastly, low added protrusion. Compared with the surface mounted doubler, a flush scarf repair minimizes aerodynamic disturbance. And we have to compare this with the other repair methods. Example, for a Criterion method, we're going to see this a load transfer, profile, stiffness, continuity, weight, and typical advantage. And for a scarf repair, it is very gradual through a bonded taper, flush or highly conformal, high when laminate is matched, potentially low added weight, structural plus aerodynamic continuity. Now we're going to compare this with the external doubler and mechanical fastener. External doubler will give as a through patch plus adhesive or fasteners, and mechanical fastener is concentrated at fasteners. This may create a step or protrusion. This usually protrusion or geometry change. Can be locally overstiff. Local stress concentration is possible. This is additionally patch material. Fasteners plus reinforcement add weight, and his simple access or repair in some cases useful for where bonding is unsuitable. And what are the key design and manufacturing controls? A key design is a scarf ratio or taper angle. This will control available bond area and stress distribution. Correct value depends on material, ply thickness, loads, and approved data. And ply orientation and sequence. Most reproduce the required structural laminate. Incorrect orientation can significantly reduce directional stiffness or strength. Adhesive bond line means the uniform thickness, correct adhesive systems, surface preparations, and cure are critical to joint performance. And it will also used to environment control. That means the temperature and humidity can affect surface preparations like resins, adhesive behavior, and cure quality. And for compaction and cure, the vacuum bagging, pressure, and cure cycle must follow the qualified process. The edge geometry means avoid sharp discontinuous. For inspection, visual inspection plus the specified entity method may be required to verify bonding and detect delamination and disbonding. For verification of stiffness and aerodynamic profile, we should keep an eye with the structural substantiation. That means the compare repair section strength and stiffness. That bond quality means verify cure, bond line quality, and absence of unacceptable voids. And for profile verification, measure the repair surface against the required contour and tolerances. The most important terminology is 100% stiffness should be presented as restoration to the original or required design stiffness, not an automatic numerical guarantee. And the limitations and when not to use it automatically. We should require a significant material removal and relatively large repair footprint because the tapir is shallow, highly sensitive to workmanship. Poor surface preparation, incorrect ply placement, void or improper cure can compromise the repair. We have to verify the thick or complex laminate may require specialized carved geometry, stepped repairs, bonded or boulder solution or replacement. And heat sensitive cores like honeycomb structures and sandwich panels require additional consideration for core replacement and moisture control. It should damage involving joint, fittings, and critical primary structures must be evaluated using the applicable SRM or approved procedures. This repair method should never be selected solely for a generic diagram. It should have a specified approved repair data control. And as a conclusion, the scarf repair removes damaged composite materials with a controlled taper and rebuilds the laminate using matching repair pelts and adhesives. Its large bonded interface and gradual thickness transition provide an efficient path for a restoring structural load transfer and stiffness. Because the finished repair can be flush with original skin, it is particularly suitable when aerodynamic surface continuity is important. The engineering statement is that for a requirement of 100 stiffness and aerodynamic profile restoration, the scarf repair is selected because it is much more capable of restoring the required original structural performance and contour when properly designed, manufactured, inspected, and approved. And for the reference, I will take as a FAA AC43214A. I take as a repairs and alteration to the composite and bonded aircraft structures. Like I take of 6 references, and here this I note to that use the aircraft or component manufacturer structural repair manual, that is known as SRM, or approved retired data for an actual aircraft repair is very useful for study about a scarf repair technique. Thank you.